Hello everyone, and hello Professor, and we are Group 9, and our topic is predicting when to arrive the non-Liao fishing port by using common filter. And first of all, to predict the arrival time, we can simply use Google Map and divide the distance between destination and myself by the current speed. But because the update frequency of the commercial GPS is very slow, such like smartphone, it is only about once every 10 seconds. So in order to know where we are when there is no signal, and at the same time eliminate the uncertainty caused by the sensor, we decide to use the common filter. So what is common filter? Most modern systems are equipped with numerous sensors that provide estimation of unknown variable based on a series of measurements. For example, a GPS receiver provides location and velocity estimation, where location and velocity are the hidden variable and differential time of the satellite signal arrival are the measurement. One of the biggest challenges of tracking and control system is provide accurate and precise estimation of the hidden variable in the presence of uncertainty. In GPS receiver, the measurement uncertainty depends on many external factors such as thermal noise, atmospheric effects, slight change in satellite position, receiver clock precision, and many more. The common filter is one of the most important and common estimation algorithms. The common filter produces estimation of hidden variable based on inaccurate and uncertain measurements. Also, the common filter provides a prediction of the future system state based on past estimation. As an example, let us consider a radar tracking algorithm. The tracking radar sends a pencil beam in the direction of target. Assume the track cycle of 5 seconds. In other words, every 5 seconds the radar revisits the target by sending a dedicated track beam in the direction of target. After sending the beam, the radar estimates the current target position and velocity. Also, the radar estimates or predict the target position at the next track beam. So the future target position can be easily calculated using Newton motion equation. And in 3 dimensions, the Newton motion equation can be written as a system of equations like this. The target parameter and this one are called the system state or the velocity. Yes. The current state is the input to the prediction algorithm, and the next state is the output of the algorithm. And you can see the above the set of equation is called a dynamic model. The dynamic model describes the relationship between input and output. And let's return to our example. As we can see, if the current state and the dynamic model are known, the next target states can be easily predicted. Well, they are not. First of all, the radar measurement is not absolute. It includes a random error, and the error magnitude depends on many parameters such as radar calibration, the beam width, the magnitude of the return echo, etc. The error included in the measurement is called measurement noise. Furthermore, the target motion is not strictly allied to motion equation due to external factors such as wind, air turbulence, pilot maneuvers, So the dynamic model error is called process noise. Due to measurement noise and process noise, the estimated target position can be far away from the real target position. In this case, the radar might send the track beam in the wrong direction and miss the target. So in order to improve the radar tracking performance, we need a prediction algorithm that takes into account process uncertainty and measurement uncertainty. Okay, so this is the block diagram of the common filter. At the beginning, we must input two state vector, and one is the state space and one is uncertainty. And then the time update is performed through the orange block, and we will get the prediction of state space and the state and the uncertainty. And next, the estimate update will be performed through the blue block, and the two calculated vector are the state vector and of the next period. So and then move on the next loop. Next, I will introduce the formula. And this is the state extrapolation equation. And this one is the predict system state vector at the time step n+1, and this is an estimated system state vector at time step n. In our case, because the acceleration cannot be predicted, we decide to put it into the input variable. And we can predict the position and velocity. So it is placed in the state vector. And finally, we assume process noise is 0. In addition, this state extrapolation equation doesn't have to be a physical formula. It can also be a linear regression or spline or intersection. And the same method has different ways of writing. For example, the prediction of acceleration can also use the differentiate the GPS position twice by Runge-Kutta methods. Thus, the acceleration term can be put in state vector. This is the covariance extrapolation equation. And according to the definition of Q of the process noise matrix, we can deduce the Q is the Q of the applicable acceleration. Then this is the measurement equation. The state vector over here represents the value obtained from the sensor. And in our case, we also assume the random noise vector is 0. And this is state update equation. The state vector here, this formula can be simply regarded as the estimate is equal to the predicted state plus a common gain multiplied by the measurement minus the prediction. This formula represents a modification to the state vector. And this formula is used to modify the uncertainty. Last but not least, this is the formula to update common gain. The common filter is an optimal filter. Thus, we will seek a common gain that minimizes the estimate variance. In order to minimize the estimate variance, we need to minimize the main diagonal of the covariance matrix. The sum of the main diagonals of the square matrix is the trace of the matrix. Thus, we need to minimize the trace of the covariance matrix. In order to find the condition required to produce a minimum, we will differentiate the trace of the covariance matrix with respect to the common gain and set the result to 0, and we will get the update equation of the common gain.
Hi everyone, now I'm going to talk about the Python simulation part. We first set up the environment. We can see that in this Python code. And we set the distance to be 235 meters. The range of time be 300 seconds with time step equals to 1. As for the frequency and the accuracy of the GPS and accelerometer, we can initialize with any integer. And here we set it to 1. This is the output graph. And this part is the arrival time. We can see that most of the result data is near the 275 seconds. And this is the velocity curve. When the above is done, we first print the graph of the GPS and accelerometer's data to become a control group of the experiment. And after that, we first test the experiment without Kalman filter. And this is the Python code. And we can see that the result tends to trust the GPS data. So the tendency of the accelerometers turns to be weird after all. And we can see that the curve of the accelerometers sum up very soon and cannot predict it. Then we use the Kalman filter to recalculate our data. And this is the Python code. And we can see that our position arrow remains stable. Moreover, the regression line of the modified position and velocity converge and are close to the real condition. And the Kalman gain here is close to 0 when the time keeps going on. So with 3 kinds of condition about the data, we can find that Kalman filter is a good mathematical model to simulate the cost time and the overall distance with accelerometer and GPS data, which prove our statement in the beginning part. And that's all about the Python simulation part.
Hello everyone, we are Group 9, and I'm going to introduce how we practice our project and the result of it. We originally want to estimate the time of biking to Nanliao, but some problems occur. First, we cannot find an app that can automatically record the position with time. Second, the GPS is not accurate enough. There are several issues which can affect the estimation result. The speed of moving objects, the weather should be considered for more accurate data. For example, the day we get the data is rainy and cloudy, which might cause some errors in GPS. Once the GPS position is updated, we need to manually record our position by using this app, Save My Location. Thus, the gravity will always have contribution to the acceleration of x and y axis because we cannot perfectly hold the cell phone horizontally. At last, we choose to estimate the walking time needed to achieve 400 meters, which makes the problem easier. And these are the two free apps we can use in this project. Both can be free downloaded in App Store and Google Play. These are data from the two apps. The GPS data on the left graph have the information of time and location. Since the sampling rate of the GPS is not high, in this figure we can see it only records 7 samples in 3 minutes. This can cause errors in the following experiments, but we will use common filter to fix the errors. The accelerometer data on the right have the acceleration values. We get 100 points per second. By feeding the acceleration data, we can get this figure. We can see that the data is not accurate because we only walk for about 200 meters. It is impossible to have the value of 700 meters, so we can speculate that the position acquired from the accelerometer is not accurate. The main reason is that we cannot hold the accelerometer horizontally without tilting. The gravity always have attribute to the moving direction. Since the formal data's error is too large, we put this data into common filter. We get these two figures. It seems to be more accurate. The filter will correct the position using the position of GPS at the time that GPS records. These are the figures of velocity and the time needed to walk to our goal of 400 meters. We can see the measurement time is not accurate in the beginning, but will get more accurate as the time passes. The following figure represents a statistical view of a measurement. A measurement is a random variable described by the probability density function. The measurement's mean is the expected value of the random variable. The offset between the measurement's mean and the true value is the measurement's accuracy, also known as bias or systematic measurement error. The dispersion of the distribution is the measurement precision, also known as the measurement noise or random measurement error or measurement uncertainty. Common filter is a good algorithm using in GPS. In this project, we have learned a lot. The main thing is that we can use common filter to predict our next step with high precision using only the current data. This is good technique using in embedded system.